Hello, good afternoon. Welcome to the DPDK Summit. My name is Kiran and I work for Juniper Networks. Along with me is my colleague Shailender, and together today we will be talking about a product which we've been working of late, and it's called the Cloud Native Router or the Juniper Cloud Native Router, JCNR for short. JCNR is a high-performance switching and routing software running on off-the-shelf x86 servers and cloud environments, and is powered using the DPDK library. Typically, in any router, there is a control plane and a forwarding plane. The control plane runs different routing protocols like BGP, OSPF, ISIS, etc., and exchanges routes with other routers. Once these routes are derived, it programs the same to the forwarding plane as a FIB or a forwarding information base. Now, packets arriving at the forwarding plane look at the FIB and then do the forwarding decisions. In JCNR, we have taken the Juniper's flagship OS called the June OS and then made it into a containerized form factor and as using it as a control plane. For the forwarding plane, we have taken the open source Tungsten Fabric DPDK powered vRouter, and with this we've integrated the Kubernetes machinery which performs the lifecycle management and simplified operations and deployments and made it cloud native. Now, the advantage of Kubernetes is that it is having a very light footprint, the bring up is fast, and then uses limited resources. This whole thing can run in any kind of cloud native environments and is an alternative for physical routers when resources are constrained or there are use cases which are applied or used only for the cloud environments. The slide shows the different cloud native Kubernetes ecosystem environments where the JCNR, which has the DPDK vRouter underneath, can run, starting from Kubernetes to Red Hat OpenShift, public clouds like AWS, Azure, Google Cloud. We also have support for VMware Tanzu and Wind River. The slide shows a more detailed architecture of the cloud native router. We have the control plane and the data plane, and there is a gRPC channel which is used to download routing information from the control plane to the forwarding plane. The forwarding plane itself has a component called the agent which is the one to establish the gRPC channel, get the routing information, then program these routes to the forwarding plane. The DPDK vRouter runs in the forwarding plane. There is a CNI or the Container Native Interface, which is a piece of software used to provide networking capabilities as soon as a pod is launched. As soon as a pod is launched via the Kubernetes machinery using the kubelet, CNI will be invoked by the CNI framework. The CNI passes the information about the pod, about the virtual network, and the other networking information to the control plane and the data plane. The data plane further uses this information to establish a vhost user communication with the workload. The workload in this case is a CNF. It can be a ODU in case of cell-side router or a UPF in case of core function or any other type of workloads. The workloads can be either a DPDK workload or it can also be a kernel workload. The JCNR can support multiple interfaces. It can support VF or it can support PF. It can run on L3 mode, which is as a router, or it can do the functionality of a pure L2 switch. This picture shows the high-level block diagram of the packet processing pipeline of the vRouter. vRouter has a set of interfaces called the VIFs. This can either be a physical interface or a pod interface or a virtual machine interface. As soon as a packet enters one of the vRouter interfaces, it is either subjected to a L3 processing or L2 processing. The picture here shows the part of L3 processing. The packet is subjected to a series of lookups like a flow lookup and a next hop lookup and route lookup, and a decision is made onto what is the corresponding outgoing interface, what the packet needs to go, and the type of header manipulations like encapsulation and decapsulation what has to be done. This decision has been programmed to it beforehand by the control plane. Now let's look at the architecture of vRouter. vRouter is designed to run both in the OpenStack as well as Kubernetes environments. It comprises of a number of L cores, what we call it the forwarding cores. The job of the forwarding cores is to get the packets from the interface queues, perform packet processing, and then send it to one or more output queues. There are other miscellaneous L cores like the netlink L core, whose job is to download the routes and next hop information from the agent and program the fib. For communication with the workloads like virtual machines and pods, it uses the vhost user library. In addition, there are a number of features in the DPDK library which it leverages. Examples include fragmentation, segmentation, metering, access control lists, bonding, etc. Another interesting feature of vRouter is how it uses a mixture of hardware and software load balancing to achieve high performance and high scalability. Most of the Intel NICs support a feature called the DDP. When DDP is enabled, the NIC parses the outer headers of the packets and then uses its hash to load balance them into the hardware queues. This is called RSS hashing. Each of this hardware queue is being polled by a DPDK L core. Since the packets are already load balanced, there is good entropy, and the L cores behave in a run to completion model and does the packet processing and then sends it to one or more output queues. In case the NIC is unable to perform a proper load balancing or there is not enough entropy in the load balancing, vRouter does something called a software load balancing, wherein the core which dequeues the packet does a further load balancing based on the inner headers where it can achieve good entropy, and then distributes these packets to other L cores which further does the packet processing and then sends it to output queues. This achieves both scalability and performance.
Thank you, Kiran. Greetings, everyone. Thanks for joining this session. Kiran gave an overview on cloud native router, and now we know that it is a DPDK application and works as a networking infrastructure layer. We have a JCNR CNI that can help pod utilize these advanced networking capabilities by configuring the interfaces inside the pod. I'll be giving an overview on how we configure the DPDK application via K8s custom resource, and we will look into a brief overview on the CNI capabilities and features. We'll go via the sample pod application YAMLs, and we'll talk about the differentiated things that we are doing. In the end, we will talk about a debug utility, which is a DPDK Info tool, which we will use in various production environments for debugging our application. This slide showcases vRouter object, which is our DPDK based data plane. You can see the kind as vRouter. We can tweak any data plane configuration by editing this CR and saving. Please note, because it is a custom resource, these configurations are only treated as a day zero configuration or an install time configuration, because the application will be restarted once you save to reflect the new configuration. For example, you are changing an interface name, right? So you have to restart a DPDK application to work on a new interface. We have a Kubernetes custom controller which watches on this custom resource and make the necessary changes into the data plane. On the right hand side, we are showcasing a DPDK specific configuration. For example, you have a CPU core mask. You're telling the application these are the CPU cores that you want to run on. This is one way of configuration. Another way, we also support the CPU manager integration, where you can just specify the number of cores and CPU manager will allocate them for you and you can utilize those. We have an additional command line args, which is very powerful, where we can tweak a lot of internal application data structures which we don't want to expose out in certain debug environments. For example, the mempool sizes, the NIC descriptor sizes you want to increase, or you want to increase the routing table size or a MAC table size, you can do those. You have a section where you can do a per interface configuration. So for example, we are showcasing a DDP configured per NIC as an auto. So this is a very specific DDP feature where we automatically detects whether the NIC has a capability to support DDP or not. So if it supports DDP, then we configure the DDP and program the flows. If it does not, we trigger the software load balancing on those interfaces. The last section highlights the application features. So for example, we are supporting a QoS. You can enable or disable, or a specific application parameter that you want to tweak, you can tweak under this. So this is how we integrate the data plane configurations with the Kubernetes via a custom resource. We need a new CNI that is capable of configuring our feature-rich data plane and control plane. So this JCNR CNI comes into the play here. It supports multiple different platforms, the DPDK for high performance and kernel and eBPF. The CNI has capability to configure multiple different type of interfaces. So we have not come across any a CNI which does that today. So we create a different CNI for each type of interface. However, JCNR CNI is unique in that way. Usually, let's take an example of an audio application where one application is split into multiple different functionalities. Some functionalities are not DPDK capable, so for those we need to provide a non-DPDK interface support. So we stitch those non-DPDK interfaces into the JCNR via the AF packet PMD today. From the functionality context, we do configure the pod network interfaces, assign IP and MAC addresses with multiple IPAMs, inject the configurations into the control plane, notify the data plane, create the interface configurations in case of the DPDK. So when the application runs, the interface comes up with the VirtIO. That means we have to pass what socket path to use, and we also provide the isolation. Let's take an example where you have a multiple DPDK application running. If we have a common host volume mount, then you have access to each other's socket, which is not a good thing and it's a security flaw. So we provide a file system isolation for those host volume pods. This slide showcases the sample pod YAML and a network attachment definition. So we have two types of network attachment definitions, where one on top is showcasing the instance type as a virtual switch, and the second where we are showcasing the VRF and the VRF target, which is for the L3 JCNR. And for the pod side, you notice we have a CNI args being passed from the pod down. This tells the CNI basically to work with and what type of interface, whether you want to use interface type as a VirtIO or you want to create and configure an interface which is non-DPDK based vETH for an application in the pod. The IP address allocation is shown as a static here, but we can integrate with any other IPAM and do the dynamic IP allocation directly. We have another key feature which we talked about, how we are doing the isolation. So we are using a Kubernetes feature called subpath expression. So if you notice, we define an environment variable, which is basically a pod UID. And on the host, it will create a volume mount in this path where run JCNR containers with a pod UID. And only this unique path based on the pod UID will be mounted inside the DPDK application pod in the mount path, which is /DPDK in the application. Now inside the pod, you will notice we have, when you do ls on the DPDK volume mount, you will see the DPDK App Config net1.json. This is the application configuration which we pass in for the DPDK application to use. There are multiple different ways to do this. You can do this via a downward API, which is also supported by us. But because we have a secure volume mount or a unique volume mount per container, we can use a JSON format and push this configuration into the same volume. So we do not have to do another volume mount for the downward API. On the host side, we are showcasing here the same two files on the host are present under a unique volume, which is under the pod UID. DPDK Info is a debug utility that reads the internal data structures from our data plane and also the internal DPDK library and displays them. So we have various different options to showcase the bond information, LACP details, mempools, stats, xstats, the alcore pinning, the application details, the DDP information. We will be showcasing few of them in the next slides. To provide the DPDK applications with the advanced networking capabilities, we use a VirtIO interface. And what we are showcasing here is to debug if there are drops on that VirtIO interface, what are the protocol capabilities that are exchanged, or if you want to look at the descriptor and the memory mapping, all those details are available and showcased via DPDK Info --VirtIO command. Here we are showcasing two commands. One on the left hand side where you can do DPDK Info -lcore. What this command does is it showcases you the mapping between which lcore is mapped to the which queue. So you can actually see if the load balance of the queue is proper, or if you need to tweak, you can tweak it accordingly. On the right hand side, we are showcasing the DDP configuration or the flows that are programmed on the NIC. So those can be queried. This slide showcases DPDK WIF stats output, which basically showcases you which packets are landing on which lcore and what is the rate at which those packets are flowing. This really helps in debugging the performance issues. When you detect a back pressure somewhere, you run this command, you can take a look which lcore is more utilized and do the necessary load balance adjustment if required.